Welcome back, everyone. So today is the fourth part of a video series where we're building a ray tracer in Rust. So in the previous one yesterday, we got up to a point where we could render a colored normal map, which was pretty straightforward around a sphere. In fact, we've got a scene with two spheres, one big large one at the bottom here that you can see, and then a smaller sphere in the middle. And so this is just this is sort of how we started. We started with this just background. We went to red. We then colored it, and that looked wrong, but we didn't pick that up. Then we got some bugs, fixed the bugs, and now we're in a good place. So the video is based around a tutorial series called Ray Tracing in One Weekend. It's awesome. I'm learning a lot from it. It's written in C++. Go and check out the previous videos. I'm doing 2 sections a day. And so yesterday we got up to surface normals and multiple objects. Today we're going to do 7 and 8. So 7 is about anti-aliasing. It's a really simple, straightforward approach to anti-aliasing, and then we're going to build diffuse materials. So I'm really looking forward to getting past this into metals and dielectrics and a whole bunch of cool things there. But I won't get too ahead of myself. So, all right, anti-aliasing. So for those of you that know, you can see, so this is a really low res image, right? This is 200 pixels by 100 pixels. And we'll render it in a larger resolution, a higher resolution at some point. But for now, it's just small. And so it's really easy to see these pronounced jaggies or these pixelated edges. Okay, and so anti-aliasing is an approach. There's a number of different approaches that help you soften those edges. And basically what you want to do is blend the foreground pixel and the background pixel in some proportion so that it looks semi-transparent. Now, the way that they've decided to do it in this tutorial is they basically just use sort of like a multiple sampling method. So they take lots of samples and they average out the rays, and then they effectively arrive at some kind of blend like that, which is a little bit unusual, but that's what they do. And so to do that, they need a random number generator. So they go through this. They generate doubles. We're going to just generate 32-bit floating point numbers. And then they also, they even build a random class. These inline random double functions. Anyway, and so it sort of builds this distribution from 0 to 1, and then it builds a generator, and then it uses that generator it returns the generator, I think. Right, so it builds this rand generator that returns double values. Anyway, and so we're going to have to do something like that. Now in Rust, thankfully, we've got something that is already pretty good. And Rust has the concept, if we look at the RNG crate in Rust, or it's the rand crate, that's where all the random number generator implementations live, or a lot of them. And so it's in the Rust book. I'll make this a bit bigger so you can see it. Yep, that's all good. So we're just going to use one of these things, and I think I can just. Oh no, I need to import it as a dependency, right? So this is my first dependency. So in Rust, that's all managed in cargo toml. And so it's literally as simple as doing something like that. In fact, you can just copy it from here and then, just do that. Okay, and so because I'm running the Rust language server, it's going to rebuild everything and then make that available for me. And so that means that whenever I want to do a random number generator, let's have a look at the documentation, see what it says. So I can use the prelude. And then I can just do rand. I can generate a random number generator for that thread, and then I can just call gen, and that by default generates a number between 0 and 1. But I can specify what type of random number generator I want. I think by just using turbo fish notation. So I think. If you're not familiar with turbo fish notation, it's a way of kind of telling I'll just find a random one here, telling the Rust compiler what you need. And so in this case, you can declare the type on the variable like this, or you can just do this. This is the turbofish. So you basically call the method, and then you put : type, and then you use the parentheses. Anyway, and so that's kind of cool, and it means that you don't need to declare it on the variable. But whatever. Anyway, and so we'll be able to do something like that to generate random numbers, which is good. And I think that should be good enough for us, because that'll give us something between 0 and 1 as a 32-bit floating point number. And then what we need to do is build a camera class. So this is, if you remember what we were doing, we had down here, we were setting up a whole bunch of kind of initial properties for, that's probably a bit big, isn't it? For where we're drawing rays from. And so now we're generalizing, I guess, to probably set up for a movable camera in the future. And so this is something that, we'll still draw rays from here, but that should be in its own class. We'll build a module for that. And then we can just update the main program, and we'll sort of start seeing, hopefully, these jaggies go blurry, and it'll give us a smoother look. So anyway, let's have a go at building this. I'm not going to start with the random stuff, because I'm just going to use the rand crate for that. I don't think I need to build my own class like that, or my own module. And then we will need a camera. So let's go and build that. So we need a camera.rs. That will be a struct, of course. And then we'll have a constructor for that called camera. And it's going to be a public constructor, remember. But that will take some arguments, surely. No. Interesting. Anyway, and then camera stores some states. So we've got origin, which is a vec3. We've got 4 of those. Whoop. So we'll have lower left corner. We'll have horizontal. We'll have vertical. Okay, and when we call camera, it's just going to hard code those values by the looks. So we'll just do camera, and then we'll have origin, which is going to be a vec3 from minus 2.0, minus 1.0, minus 1.0. In fact, I'm sure we've already got that somewhere. It's probably exactly the same. Yep. So let me just pull this from here. Actually, be something like this, right? Oh, without the equals. Not quite so easy. Now, I got myself into trouble in the last video by just assuming that this was correct. And we'd actually changed the code, or at least the documentation. The tutorial had different code, so I'll double check all the values here. Minus 2, minus 1, 1, 4, 0, 0, 0, 2, 0, and then origin is at 0, 0, 0. Good. So that looks pretty easy. And then we're going to have another one that's called pub function getRay, which will obviously have a reference to self. And then we'll have 2 values, and this will return a ray, which has got self origin, lower left corner plus u times by self horizontal plus v times self vertical minus origin, self origin. Apparently. That's pretty neat. Oh, actually, that should just be like that, and then this should return ray, and camera should return camera. Now I will need to use create ray here, and use create vec3. Okay. So that's kind of the camera module, isn't it? So we get this hard-coded camera with hard-coded in the sense that the coordinates and all the state configuration of the camera is hard-coded. And then when we want to, on the camera, we just call getRay. And so getRay on the camera will just keep shooting rays off for us to UV, wherever we're trying to draw on the screen. Okay, looks good. And then we'll go back to main, and then what we'll do is we'll use it. So this will make sure that everything's working or not. Use camera, which is not public, and we also want that'll do. So we'll make this public. Okay, so we've got a camera now. Now what we want to do is we want to change our main. And so, okay, I'm going to rename these because these are terribly named. If I can ever type. So that'll break all the references there. That's okay. So we want width, height, width, where else was I using it? That's it. Good. And then what we're going to do is we're going to introduce this new thing called NS. Now the NS is the number of samples. So we'll give it a better name for our purposes. And it should be, these will probably be constants at some point, or we'd probably parameterize a render function or something, draw scene function. And so, so these would be passed in as parameters probably. But anyway, and so what we'll do is we will have the same details. We don't need any of this stuff anymore because this is going to be built into the camera. Got our list of hittables. Okay, and then what we want is a camera. So let camera equal, we'll call it cam, equal camera. Now we've got a camera, which is good. Like that. And then we will, what are we changing? So as we're looping across, as we're scanning across the screen, we're going to introduce a new vector called color, I guess. Yep, color. All right, so let color equal, call it col equal, it's just a new vector, right? I can do default now. So as we do that, then what we're going to do is we're going to loop through all, so for S in samples, okay, we still want all this float stuff, and then we still want the ray, we still want the color. Cool. So we just need to do what's wrong with me? Still want all of this here, I think, not samples, for S in 0 to samples. And then, so we're starting at 0 and we're going up to samples -1. And in Rust, if you wanted to include the end, you do equals. I think it used to be this, but I think it's been updated to be ... equals now. But we don't want samples, we just want samples minus 1, counting from 0. And then we still do, this is where we need to introduce some randomness. Okay, so we need to introduce randomness here and here. And then when we build the ray, we just call cam now. So that makes sense. So let's do cam get ray, u, and v. That should be correct. No. Use of moved. Okay. So this will need to be a reference, which means that this will need to be a reference. So we'll borrow it, basically, we won't move it. And then cam.getRay, that looks fine. And then pointer parameter, we don't need pointer parameter anymore. It wasn't even being used. And then here we'll do plus equals color and worlds. Now plus equals isn't implemented. So I could probably just do color plus color, can I? I mean, it should just be vec plus vec. That makes sense. But I want to declare it there. Color is declared outside the loop, which means this needs to be mutable. It would be nice to have, add a sign. And in fact, we might go and do that later, but it's pretty easy to do, right? It's just overriding another trait. Okay, so this is all looking pretty good. And all right, and then we also need to divide it down here. So color is equal to color divided by ns. Oh, s. Huh? Sorry, samples. Okay. But as a float. Okay. That looks okay. S isn't used, but why? Okay, we actually don't need S. So just to get rid of that, in Rust you can just use underscore for things that aren't being used, aren't being referenced. So this still gives us a loop without worrying about assigning anything to S. And then that looks pretty straightforward to me. Okay, so the last bit we need to get right is this randomization. Now, because we're already using the rand crate, we should just be able to do something like this. Now, if we go back to the documentation, we need to build, well, I don't think we need to build this, but we will. So we'll do, we'll create a, outside of the loop, we'll say let RNG equal rand thread RNG. Now thread RNG, okay, will retrieve a lazily initialized thread local random number generated seeded by the system, which is nice. And so this is kind of how we'll call it. We'll do thread RNG.gen : type, and that's the turbofish, right? That's nice. So we'll do something like that. But we'll actually, I wonder, we probably don't even need to do this, right? We could just call it like this, thread RNG. Or cached locally. I wonder what the difference would be for caching. Probably nothing. Anyway, that's fine. So what we'll do is we'll still do a cast for I, because I is U size, probably. Oh no, it's I32, right? Yep. Okay. And then what we're going to do is we'll use the RNG. So we'll say the random number generator.gen. Now we want float 32, and then we still want to divide it, something like that anyway. Except it's kind of confused. Oh, like that. And gen not found. So I probably need to import the prelude, maybe. Excuse me. All right, let's just do that. Let's go. Oh God. Let's go. We'll do use. Excuse me. Prelude. All of it. Okay. So what we want to do is we want to add this first. So just to avoid operator precedence problems, it's going to be something like this. Plus RNG gen float 32. It's getting a bit ugly. So that's done. And so I think that's all we need to do. Let's just double check our code here. Get ray, color. Looks good, doesn't it? I think it looks okay anyway. So I think we're ready to try and run it again. So when we run this, if we've done everything right, we should start seeing some blurry edges. So this is what it looks like now. So let's try reloading. Okay, well, that's worked. So you can see it's blurred it quite well, hasn't it? Which is rather nice. It's done a good job of the larger sphere too. Make sure my monitor doesn't turn off here. So it looks reasonable. Good. So that's section 7 done. So that's all they're doing for this part, right? So they're not really doing anything sophisticated here, and they're not doing any other, like there's all this other sampling they could be doing, but they're not. They're just generating some. They're doing 100 samples. They're generating 100 of those samples, or we are, and then we're building 100 of those. We're looping between. We're generating 100 of those. So we've actually slowed our program down by 100 times here, right? This inner loop is doing 100 times more work overall. But then we're adding all of the different random variables, and so we're getting like a nice, I guess it would be an even distribution. I guess what random distribution does rand give in Rust distributions. Just how random is rand? Someone to have built a pretty graph. Anyway, whatever it is, we've sort of averaged that out nicely. All right, so now what we have is the section on diffuse materials. So our material here looks pretty. I mean, we don't even have the concept of materials, right? We're not doing anything apart from coloring in the normal map, right? So the only thing that we're looking at here is an RGB value that maps to the way that the normal is on the object, and so And so anyway, that's not particularly useful, right? We want to actually start playing with something. We're not going to put textures on this thing, right? There's no geometry to put textures on. But what we want to do is kind of like simulate what light does when it's hitting an object. And so this is where we start getting into a whole area of stuff that, again, I know nothing about. But from a physics sort of perspective, diffuse objects look matte. And the reason they look matte is because the light rays that are bouncing off them and reflecting back are scattering. And in this case, what we're doing is we're building a sort of a scattering algorithm that's completely random. And so it's going to, it's basically going to sort of simulate taking all of those samples and then doing some kind of randomization on that. So if we look at, what are we doing? Okay, diffuse objects don't emit light, that don't emit light merely take on the color of their surroundings. But as they modulate that with their own intrinsic color. Light that reflects off a diffuse surface has direction randomized. They also might be absorbed rather than reflected. The darker the surface, the more likely absorption is. That's why it's dark. Any algorithm that randomizes direction will produce surfaces that look matte. One of the simplest way to do this turns out to be ideal. Right, so I still don't know what a Lambertian surface or a material is. I guess we'll find out. Oh, it's reflectance. It's an ideal diffusely reflecting surface. Okay, there you go. So an equal percentage of, I don't know how that might work. But anyway, we'll work that out later. And so in this case, what we're going to do is we're going to pick a random point from the unit's radius sphere that is tangent to the hit point. So as we pass rays through, we're going to, where the hit point happens, so where the ray intersects with the surface, we're going to build a radius sphere that is tangential and send a ray from the hit point to the random point S. Okay, so if you think about it, effectively we're going to build a little unit sphere, simulate that. We're going to have the hit point, and then we're going to send a ray from that hit point, which is kind of where the other sphere is kind of attached, and we're going to basically just randomize points on that unit sphere. And so this should give us, I guess, reasonably random. It's not going to be fully random though, is it? I mean, it's going to be random, but it won't be, evenly distributed. You would imagine that you'd get, it'd be less likely to send rays to the side than it would be to the top or the bottom. I don't know how this will work. Anyway, we'll work it out. I guess it can't be because at the bottom, yeah, that'll be interesting. But anyway, so this is the little sphere that we're basically going to simulate, all right? And that's the actual sphere, and that's the hit point down here. And so we'll basically get the normal, the unit sphere around it, and then from the hit point to any random point on this sphere, we'll generate a vector, and that vector will be, I guess, the direction of the ray. So we need to build something that does random in unit sphere. So this is effectively going to do that for us, I presume, which is good. And then, so that's going to return a vector for us. Okay, so that's going to take a long time to, well, anyway. And then we update the color function to use the new random direction generator. Cool. So the color function currently does, what does it do? If the world is hit, it returns this hard-coded vector. Right. Which is the normal. Okay. Which will be somewhere in between 0 and 1, presumably. Well, actually, between 0.5 and 1. Is it? Like if normal... Anyway, it doesn't matter. So And then that's going to give us that, right? That looks pretty nice. Okay. All right, so let's go and build this this other function. So this is the thing that we need to get a random from the hit point to any random part on the sphere. So we'll do random in unit sphere. Now, what's it going to return? It returns a vec3. Now we've got p, which is going to be it's going to be this. We've got a p. Okay, so that'll satisfy the compiler. Now, what we need to do in here is, so this thing's gonna, this is interesting. So it's gonna loop forever until p squared length is greater than or equal to 1. And then when it is greater than or equal to 1, it's going to return that thing. And p is going to be p squared length. So it's going to just do random, it's going to do a random vector, and then it's going to subtract that from 1, 1, 1, and times it by 2. And when it's greater than or equal to 1, it's going to return it. All right. So we can do while. Oh no, we can just do loop, and then we'll do p. So this is be mutable, and we'll do p is equal to 2 times by this vector, which is going to be, more random stuff. Let's just do another one. It's probably not that efficient, but we'll just copy because we're lazy and we just want to get something going. So we've got a new random number generator in there, and then we'll still be able to do this random gen float 32. So we'll do, we need to do that here. So we'll do RNG gen float 32. And we'll need to do that 3 times. Okay. Float 32 gen float 32. Okay. And then we want to minus, I'm missing the method, the call. And then we want to minus a new vector that is just unit length. Okay. So that's what it is. And then what we say is if p dot squared length. Aha, we don't have squared length, right? So remember we were building out our vec3 class as we went. So squared length is basically is literally just squaring each component, and so we need to implement that. So we'll go back to our vec3 class, and we need a new method here called squared length. Which returns a float. And then what we do is we go, sorry, of course it needs self. Then it will be self.e. Oh, this is going to be laborious, but anyway, we'll get there. Times by self.e 0. Okay. So we'll just we'll yank that and we'll just go plus, is it? Yeah, plus, plus. And we'll come back here and change it to 1. Is that right? Yeah. And 2. Okay, so that should give us the right thing. So we've got squared length is just, well actually it's just the length squared. We could have just done that, couldn't we? But I guess this is probably faster. So we need, yep, that looks fine to me. I haven't made any mistakes there, have I? All right, and then we'll go back to here and we should have squared length now. And squared length in this context, what are we using it for? So we want it to be greater than or equal to 0. Oh, sorry, 1. But if it's not, okay, so if it's less than 1 in that case, then we want to return p. Otherwise, we don't finish, which is a bit weird, isn't it? It's just mismatched types. Return p. Okay, should be okay. So we loop forever. Well, we keep looping until we get something where p squared length is less than 1. And then if it is, we return it. P is 2 times by this random vector minus this unit vector. So that's what we're looking for, right? So the unit vector is basically representing the center, the radius, the sphere, sorry, the sphere. Okay. Okay, all right, let's give it a go anyway. So we go back up into color, and then when we have world target, so now we can get rid of this hard-codedness, and we can say let target, which is going to be a vec3, equal to rec p plus rec normal plus random unit in sphere, random in unit sphere. Okay, and then what we're going to return is 0.5 times by, we're going to recurse color, right, okay. So we're going to build a new ray, which is that needs to be a reference anyway. So there's this. Okay, so this thing is going to return. So this is going to recurse, right? And then it's going to approach something, right? So what's going to, if it hits, then we recurse. We go smaller. We halve it. We halve the vector. Well, no, hang on a second. Sorry, we don't halve it. Well, we sort of do. Well, half times color. We build a ray which has the hit record P, so direction, target minus that. So ray takes Remember, array takes, I should have named this better, but origin and direction. And so in this case, the origin starts from the hit record. So it's a sphere about that origin, so where it's hit, and then target is basically the hit record. Rec P. Hang on a sec. Rec P is plus random in unit sphere. So why isn't P used? Oh, okay, it's never read. Well, it's returned. Anyway, I'm going to go through the intuition behind this later, but let's just see if this actually works. So what we're going to do is probably run it. It's taking ages. Taking a really long time. Did something. Gave us some output. Let's see what it looks like. Open recent out. Okay, so we should get nice. Okay, that looks about right. Wow, we're getting some really beautiful soft shadows here. That's pretty neat. Cool. So so it's pretty dark, but it's not as dark as the picture. That's interesting. But that's okay, I think. I don't have a massive problem with that. Let's run it again. See what happens. It's really slow now, isn't it? Because it's doing all this. It's doing all this looping. Like this loop in here, where it just loops forever until it finds this thing, and then the recursion as well. God knows. Anyway, we'll go. I wish I could profile Rust code, or like step through it rather. Well, profile would be handy. Profile and step through, debug and step through. Profile would be handy. Anyway, so we've got some dark sphere. It looks quite beautiful though, right? So it's still, I mean, we've got our anti-aliasing doing a bit of work. You're still getting some sort of semi-random stuff here. But then what I really love is this, we're starting to get shadows now. And nice soft shadows. Which is just freaking beautiful. Anyway, so we're starting to look like a real ray tracer, kind of. For a very simple scene. All right, and then it's saying, what's it saying? Picture is very dark, only absorbs 50% of the energy. Almost all viewers assume that the image is gamma corrected. Oh. Meaning the 0 to 1 values have some transform before being stored as a byte. There are many good reasons for that, but for our purposes, we need to just be aware of it. To a first approximation, we can use gamma 2, which means raising the power to the color to 1 over gamma, which is like, is it the gammath root? Yeah, so gamma 2, okay, which would be to the half, which is a square root. Okay, interesting, cool. And so that's easy then. So we're going to just square root each one. So for us, down in here, we could just do, they create a new one, a new color. They assign it to color. Let's do that. So we want color is equal to vec3 new, and then it'll be whatever color dot r was, square rooted. And then it'll be color dot .b square rooted, and then color, color G, .b square rooted. And then that should give us a new color. Then we should run again. We'll get some quite slow performance here, and so that should just lighten the image. So let's have a look at what we see now. Yeah, beautiful. So this looks, what does it look like? Concrete, maybe? Don't know. It's a nice matte sort of diffuse grey color, which is really good. Again, it's lighter than the maybe it's GIMP doing that. I don't know, but we're still getting these beautiful shadows, and we're getting this nice kind of diffuse looking matte surfaces plus anti-aliasing. Again, at really low res, but hey, it works. All right, so that was a lot faster than yesterday. I don't know how much time we've been running, not that long. And I'm going to finish here. So I'm just really committing to doing 2 sections a day. So we've done overview all the way up to diffuse materials, which is cool. Now, I'm starting to see that doing it this way isn't really getting deep into the intuition behind the maths or actually understanding the geometry that's going on here. So I think I need to go through and think about this more deeply, and then maybe do a session on that from my understanding, which would be a bit hard without a light pen or something. I'd just be waving my hands madly. But anyway, I think I need to do that, and I need to do that sooner rather than later. The next one, which we should do tomorrow or the day after, probably tomorrow, is metals. So this is going to be cool, and I can't wait to look at this, because I think we'll end up with some pretty beautiful looking effects. Wow, that's interesting. That looks like a translucent thing. Ooh, that looks nice. So you get more reflection. Nice. Okay. Well, anyway, and then dielectrics, like water, glass, and diamonds. Definitely diamonds. We want diamonds. Oh, this is huge. Okay, so this will be a really long one. So I think metals is easy, but who knows? It looks quite a long one, but maybe it'll be another long video. And then what do we do? We're getting ahead of ourselves, but positionable camera, so we can move it around, and then defocusing, like depth of field or something. Ooh la la. Anyway, awesome. Look, I'm going to stop here again. We've got our beautiful looking image here. The code works. It's slow, but that's just because it looks pretty inefficient the way we're doing this. So what I'm going to do is, I'll commit what we've done. So we'll add all the source code, and then we need to track cargo. Actually, we'll add cargo, and we'll add the data too. Cool. And then I'll just do a commit. Git commit added, what are we going to call it? Diffuse materials. Okay. Added anti-aliasing. Is that hyphenated? No. Git commit added anti-aliasing and diffuse materials. Diffuse is only one word, right? Oh, one T. Goodness me, I can't even spell. 2. Diffuse materials. Oh. What? Oh, that's annoying. I've been mucking around with, so it looks like it's using a new Git. Oh. That's not great. Git config global user email. And git config global username. Okay. That looks okay. All right, so I've pushed the code. Now I have the GitHub repo. Remember, don't forget about that if you're playing along. You'll see a link here. We've got a markdown file, links off to the tutorial. We've just uploaded our data here, which is fine. And then the source code here, right? So we've got the camera module in here now, and everything else that we've been writing in main. Main's starting to look, it's only 100 lines, so it's not too big, but it's looking okay. So please follow along there if you want to, and check out the code and play around with it, and tell me how I could be doing it better. And then we'll go to that next section tomorrow or the day after. Probably I'll start tomorrow. We'll see if I get the video done on doing metals, and yeah, I can't wait to get down to the dielectrics. That's where it starts getting really cool. I wonder if we model internal reflections and things like that. I don't know, probably not. Who knows? Anyway, so thanks heaps for joining. A shorter video. We took our time though, and please follow along. Join me in doing this if you want to do this or learn more about this topic. And like the video, subscribe, and I'll see you in the next video. Thanks heaps.